Hello, everybody. So, today we are going to be talking about something called the Chatelier's principle, and it's a deeper dive into our conversation about chemical equilibrium. I haven't finished, as of this time that I'm recording this video, I haven't finished the today's assignment slide. By the time you're seeing it now, there should be a link to the screencast and a link to the exit ticket. Still have to make the screencast, so that'll be up. All right, so before we talk about Le Chatelier's principle, let's just quickly kind of reintroduce and review what exactly it means for a chemical system to be at equilibrium. So, in reality, many reactions never actually finish. So when you see that single right-sided arrow like you're used to, what that's basically telling you is that all of the reactants proceeded to become products. The reaction's done. But most of the time, doesn't actually work like that. Most reactions are actually reversible, which means they can go both backwards and forwards between reactants and products. So here, even in the simple formation of water, you're seeing that double-sided equilibrium arrow, which is telling you that basically at any given time, hydrogen and oxygen are reacting to become water, and water is dissociating to become hydrogen and oxygen again. So the goal of most systems is to establish an equilibrium, where the rate of this forward reaction, so going to the right is often called the forward reaction, is equal to the rate of the reverse reaction, going to the left. And equilibrium just means balance. So these guys are becoming this guy at the same rate that this guy is becoming these guys. And that's all that means when I say equilibrium. All right, so where does Le Chatelier's principle come in? Well, once a reaction reaches chemical equilibrium, it likes to stay there. Changes in things like concentration, pressure, and temperature can threaten a system's equilibrium. And a system is going to do whatever it can to overcome these stressors and maintain that equilibrium. And the whole idea or principle behind this is Le Chatelier's principle. This is Le Chatelier right here. That's the picture I have on that first slide. All right. So we're going to talk today about what happens when you change concentration, pressure, and temperature of a system. I'm going to say the word shift. What I mean by that is if a reaction is shifting to the left, if you can see me, I'm doing the air quotations. If a reaction's shifting to the left, it's shifting towards the left side of the chemical equation, so towards the reactants. And if it's shifting to the right, it's going towards the product side. All right, so if I have this chemical equation right here, the generic one that I picked, and all of a sudden I were to add more nitrogen to the reaction mixture, what I'm doing is I'm adding more concentration to my reactants. And by doing that, I'm threatening the equilibrium of the system because now potentially I have a lot more reactants than products. And in order for a system to be at equilibrium, I want my little seesaw to be even, but right now the reactants are outweighing the products. So the system is going to need to shift or change in some way to maintain the equilibrium that all of a sudden has been disrupted. That's where Le Chatelier comes in. Luckily, my system is able to balance itself in order to maintain equilibrium. I've added more reactant, more N2, so I've added it to the left side of the equation. In order to counteract, I need to add more to the right, right? So the system is going to shift to the right in order to produce more product and restore equilibrium. Basically, the reaction shifts away from the side where additional concentration has been added. So if I had added more of NH3, which is ammonia, this is actually the Born-Haber cycle, which is used to create fertilizer. If I were to add more ammonia, since it's a product and it's on the right, the reaction would shift to the opposite side to balance. So the reaction would said to shift to the left. All right, so that is what happens when you change in concentration. If you add concentration to the left, you're going to shift to the opposite, right to the opposite. If I were to take concentration away from the left, and all of a sudden my reaction box were to become smaller, what do you think would happen? Yeah, the reaction would shift towards the reactants again. All right, so that is concentration. Now let's talk a little bit about dealing with a change in pressure. So what would happen if I were to decrease the pressure of a system? And this is taking us back to gas laws. So if I were to decrease the pressure of a system, and I could do that, for example, by if I had my chemical reaction mixture reacting in this piston right here, I could decrease the pressure of a system by increasing the volume. And when I increase the volume, I am having less collisions between particles and with the sides of the reaction vessel. So the reaction's actually occurring at a slower rate, because remember, more collisions means a faster reaction. If I were to push down the piston and decrease the volume, I would have more reactant collisions and the reaction would proceed at a faster rate. Anytime I change pressure, concentration, or temperature, I'm messing with the equilibrium of a system. Now, according to Le Chatelier, system doesn't like that, so it's going to try to counteract what you've just done. So we're just going to pretend that we're looking at this reaction right here. This is a covalent compound, dinitrogen tetraoxide becoming nitrogen dioxide. So if I were to put this reaction mixture into my vessel and put a piston on top, and if I were to suddenly increase the pressure of my system by decreasing the volume and bringing down this piston, the gas particles, like in the previous picture, are going to start colliding more with the sides of the container as well as with one another. When they do this, again, the rate of the reaction is going to increase. So we want to counteract this to maintain equilibrium. And so the question that you need to ask yourself is, which direction is the reaction going to shift in? Is it going to shift to the left towards the reactants or to the right towards the products? Well, if you're increasing the pressure and making things a lot more crowded, the reaction is going to shift to the side with less moles of substance. I'm going to add that in now that I'm looking at that, of substance. And to figure out which side has less moles, you're just going to look at the coefficients. So in this case, this guy has a coefficient of 1, whereas this guy has a coefficient of 2. This guy's got more room to take more particles and increase pressure. So the reaction is going to shift to the left towards the side with less moles to alleviate that issue. So if I were to decrease the pressure by increasing the volume, I would actually want to shift the reaction toward the side with more moles. So in that case, it would go over here. And then the very last thing that I want to talk about is dealing with a change in temperature. So once again, we're just going to use this reaction right here since I've already introduced you to it. If I were to tell you that this was an endothermic reaction, just think to yourself for a second, which side of the chemical equation do you think the heat would be on? So the endothermic reaction means that it's taking in heat. If I'm absorbing heat, the reactants are absorbing it. All right, so technically the heat is on this side, so I can actually rewrite my equation as heat plus N2O4 yields N2O2. If the reaction was exothermic and it was letting off heat, it'd be letting off heat here in the products. So endothermic, heat's on the left, exothermic, heat's on the right. All right. So that's the first piece of the puzzle, is usually the question will tell you or ask you, all right, so this is an endothermic reaction or an exothermic reaction. The first thing you have to do is figure out, well, which side of the heat which side of the reaction is the heat going to be on? Sorry. All right, so if I were to increase the temperature of the reaction, I would basically be adding more reactant to the left side. So once you've figured out where the heat goes, either the left or the right, you can basically consider it to be a reactant or a product. In this case, because heat is on the left-hand side, it's basically a reactant. which means that if I increase the temperature of the system, I'm going to want to act in the same way that I would with concentration and shift it to the opposite side. So if I'm adding reactant, reaction shifts to the right. If I were adding product, reaction shifts to the opposite side, to the left, to maintain that equilibrium. So likewise, if I were to decrease the temperature of this reaction, I would be losing reactant, so the reaction would shift to the left towards the reactants. I do ask that after you've listened to me talk, you watch this quick summary video. I think it's really good. I think it'll help you with the exit ticket, and it's worth the watch. And then, and I put it in a different color so you know that it's optional, if you're still struggling, this is a really great additional video. I like videos because they have animations that I do not have the technical savviness to do right now. So go ahead and watch these two. All right. And then when you're all set, try out the exit ticket and let me know if you have any questions. Have a nice day.